Hey CTM students and anybody else who might be watching, welcome to lesson 10.2. It can be found on these pages, and if you want to check out some of the new vocabulary, here it is. Not nearly as much as the last lesson, but we're going to be focusing more on figuring out whether things are or are not groups in a finite sense, and make sure you're using those extra examples. There's, especially with this lesson, a lot of this stuff might be kind of like brand new stuff for you, where in a sense, kind of like the chapter we had on adding in different bases and adding in different kinds of number systems, like the Mayan, like the Egyptian. I feel like this is kind of a twist your brain, wrap your mind, take your mind out of the box, and kind of wrap your mind around some new concepts here. This one may take a little bit of extra thinking, a little bit of extra practice, and pausing and rewinding to really grasp. So make sure you're doing that if you need to, and checking out those extra examples in the book. But let's get started on finite mathematical systems. So first of all, let's define what a finite mathematical system is, and then let's move on from there. So finite mathematical system is just like it sounds. It's a mathematical system that is finite. It has an end to it. It doesn't keep going on and on. There's not an infinite number of elements in the system, in other words. So it's a mathematical system with a finite number of elements. And just wanted to bring up 10.1, the completed version of that real quick, where this was our last lesson. We had infinite mathematical systems, where they had an infinite number of elements. It kept going and going and going. So we had things of that nature, where we had the whole set of real numbers and the set of rational numbers within the set of real numbers, and so on. This, we're dealing with systems that don't have that ellipsis, don't have that dot dot dot. They actually have an end somewhere. So let's first consider the following. So this is example 1. Consider, I'm going to say not that, but consider clock 8 arithmetic. We'll talk about what I mean by that in a second. Consider clock 8 arithmetic with elements 1 through 8. 1, 2, 3, 4, 5, 6, 7, and 8. What we're going to do is make an arithmetic table for the operation addition. We're going to be adding these elements together. And then determine if the system is a commutative group. So commutative group. So if it's just a group, we're checking 4 things, but if it's a commutative group like this is asking for, we're checking 5 things. So under addition, commutative group under addition. So what is clock 8 arithmetic? What does that mean? What do I mean by that? So right here we have clock, this is basically clock 12 arithmetic, like we're used to seeing. So you add 1 plus 3 and you get to 4 o'clock. If you're at, let's say, 7 o'clock and you add 6 hours to that, you're not at 13 o'clock, you go this way, you go to 1 o'clock. So this is kind of like what we're doing. This is exactly like what we're doing, but we're going to do this with clock 8. So we're going to pretend the clock now has 8 hours on it instead of 12 hours. And so let's, off to the side in the column or in the space that you have in your column here, we're going to draw our own clock, and we're going to make it clock 8. And so how do we do that? Well, we can just put basically split it up into fourths, and then split each one of those sections up into two sections. And then we're going to label it like you see here. So this last digit, this would be 1, 2, 3, 4, 5, 6, 7, and then the last digit would be 8 instead of 12 like it is in clock 12 arithmetic. And then you're starting over again at 1, 2, 3, and so on. So up here, this is where our binary operation goes. So for us in this case, it's plus. It's an addition here. So these spaces, you have blue lines most likely on your paper. You can just use those. But I just put some yellow lines to help me keep things straight. And if you want to put columns, you can. They're not necessary. But if you have trouble keeping things straight, literally keeping things straight, you might want to add some columns here. So I'm going to put clock 8 elements in here, 1 through 8, 1 through 8. Now what would 1 o'clock plus 1 extra hour be? It would be at 2 o'clock. Similarly, 1 o'clock plus 2 extra hours would be at 3 o'clock, and so on. So 4, 5, 6, 7, and 8. We can't have 9 though in clock 8 arithmetic, just like in different bases you can't have something that doesn't belong in the base, like base 6. You couldn't have a digit of 7, you couldn't even have a digit of 6. Here we can have a digit of 8, but we can't have a digit of 9. So if you go to 8 o'clock, and then you add 1 more hour to that, or if you're at 1 o'clock and you add 8 hours to that, that's probably a better way to say that, you end up back at 1 o'clock. So I would put a 1 right here. In a similar way, 2 o'clock plus an hour is 3, 4, 5, keep going here, 6, 7, 8, and then you get to here, 2 o'clock plus 7 hours gets you back to 1 o'clock, 2 o'clock plus 8 hours gets you back, goes one time around the clock, gets you back to 2 o'clock. And so let's fill out the rest of the table like that, see if you can fill it out without looking up here even. I bet you could, but just double check up here if you need to. And then when you're all done, definitely double check and see that you did it right if you're going about it without looking up here. So 6, 7, 8. And you may notice some things as you fill in your table. You may notice some symmetry, and there's definitely some symmetry in clock 8 or clock anything arithmetic. And then I want you to get out a different color at this point. So I'm going to use red for this. You can use whatever color you choose, just not the pencil that you're writing in, or not the black that you're writing in. So I want you to circle this middle diagonal. Trying to be careful not to circle these other ones. And let's make a little note of this off to the side here. This middle diagonal, we call it the main diagonal. It's probably what I should have said, not the middle diagonal. It's the main diagonal. And there's a little trick that you can use with the main diagonal. So let's write down this trick too. The system, I'm not saying it's a commutative group necessarily, but the system itself is at least commutative. Step 5 is good, in other words, in the 5 steps you need to check. So system is commutative if it's symmetric, and you could say across, but the language that the book uses is about, so we're going to say about the main diagonal. So write that down in a different color, have this circled in a different color, and just look at that. Let's see, 7 is 7, that's symmetric, 6 and 6, then 5, 5, 5, 5, 4, 4, 4, 4 is the same over here, 3, 3, 3, 3, 3, 3, and so on. That continues. This is a commutative system. The whole group, I'm not saying it's a commutative group yet, but it is a commutative system. Step 5 checks. And so you can do that with each one of these. And why does that work? Well, you're basically saying 2 plus 1 is the same as 1 plus 2. And 3 plus 2 is another example. Is that the same as 2 plus 3? Yes, it is. So if it's symmetric, that always works out. So we need to now check and see, we've done the arithmetic table for operation addition, that's all here, it's part of what we need, and then now we need to determine if the system is a commutative group under addition. So let's check that out and see. So let's answer that question now. So is it a commutative group? Question mark. Alright, so is this the case? So what do we need to check? We need to check those 5 steps again, looking here at 10.1, going back to that, there they are. So this is a set closed. Does it have an identity element? Does it have an inverse? Is it associative? And then also, is it commutative for that commutative group? So we're going to go through the steps, and we're going to not write out the whole thing. It is set closed. We're just going to use these underlined words and go from there. I'll teach you a little clever way that I'm using to help me remember what goes where, what comes first, second, and third. So first of all, we need to decide if the group has closure. Take out your different color, and then off to the side I want you to write this in a different color. This is the C part. And I'll just tell you what my little clever way to remember this is right now. So I'm going to go CIIA. It's like the central... I forgot for a moment what I was remembering. We're going to remember central insanely intelligence, or insanely intelligent, I guess would be grammatically correct. Central insanely intelligent agency, and then I don't have something for C. I got to come up with something for that. But the CIIA basically is what we need to check, and then if it's commutative as well, we need to check an extra C. So check for closure first. Basically what you need to do is look at the table and make sure that all the elements listed in the set of elements are the only ones that show up here. If there's anything brand new in the table, then you know it doesn't have closure. But since there's nothing brand new in the table, we know that this has closure. So would you say yes or no? You would say this checks out because each element in the table is an element of the original set. So I'm kind of going back and forth. This is still with example 1, so I just don't have enough room to write it all in there. So here's the original set. Everything in the table is an element of that original set. And so this, in my different color, I'm going to put a check mark by the C, the closure checked out. So let's check step 2. Step 2 is to check the identity. Is there an identity element in this group, or in this mathematical system? We're trying to check and see if it is a group. So is there an identity element in red? Put an I. So no check mark by that yet. We need to check and see if it actually has an identity element. So to see if there's an identity element, basically you need to just look at one of the columns and see if there's a column that looks exactly like that. And if you go far enough here, that column looks exactly like this column. You need to do the same thing with the row. So is there a row that looks exactly like this? Yes, there is. That row looks exactly like the last row. That means the identity element is whatever shows up right there. So the identity element, is 8. If you add 8 hours to something, that should make sense based on the clock here. You add 8 hours, you get back to where you started. If you're at 4 o'clock, you add 8 hours, you're back to 4 o'clock in this clock 8 arithmetic. So the identity in this case is 8. So adding 8, and I will I'll box that in. That's the identity element. So adding 8 to any element gives the same element you started with. And then, as a reminder, we would just look in this table, we would just look at the last row right here and the last column right here. We can verify that 8 is in fact the identity element because they're all the same as the row you started with. So see the last row slash column in the table. It's just a little reference back in our notes to to check that when we look at this later to help us as a study guide. So close our identity. Now we're checking for an inverse, and you'll notice, nice thing about this, they go in alphabetical order, at least the I's do here. So the I, yes, C comes before I as well, but C, and then identity, ID comes before I, and so just remember them in alphabetical order and you'll be good to go. So is there an inverse for each element? We need to check and see if there's an inverse for each element. The inverse for each element would be the number that you add to it to get the identity element. So what do you add to 1 to get to 8? You add 1 plus 7 to get to 8. So looking at the clock itself, 1, what gets you back to where you're supposed to start here? 1 plus 7 hours will get you to 8. If you're adding 3, what gets you back to 8? 3 plus 5 hours gets you back to 8. So here's 3 plus 5 gets you back to 8 right here. So basically we're looking at this diagonal going this way and saying, okay, it's 1 plus what gives me 8, 2 plus what gives me 8, and so on. So let's write those things down here. 1 plus 7 is 8. We need to check and see that each element has an inverse element that gets you back to the identity element. So 3 plus 5 is 8. 4 plus 4 is 8. So far this is just basic arithmetic for us. 5 plus 3 is 8. 6 plus 2 gives me 8. 7 plus 1 gives me 8. And then here's a little tricky one. 8 plus, you can't use 0 because that's not a member, that's not an element of the set in question, but you can say 8 plus 8. So if you start at 8 and go all the way around, add 8 hours to 8, you're back to 8, back to the identity. So 8 plus 8 in this system also equals 8. So let's write a little note off to the side here that every element has an inverse that adds to it to get the identity element, which is 8. So identity element 8. So let's write that off to the side here. That goes with the inverse here. So that is true. So let's check out, let's put this other I here. So CIA, this the Central Insanely Intelligent Agency, we've checked that. So now we need to check the A part. In other words, we check what the A stands for is the associative property. So we need to check and see if the associative property does in fact work out. So we would need to check, or we should be thinking of checking every single case. It has to work out every single time. But hopefully you can see here, looking at this, any clock arithmetic is always going to work out. If I take 1 plus 2 and then add 3 hours to that, so if I start at 1, add 2 hours to that, I get to 3, and then I add 3 more hours to that, I get to 6. That would be the same as saying we're taking 3 plus 2, which would be 5, and then adding 1 to that, you get to 6. So that's going to work out every single case. You can take any 3 numbers in this system, add them together, you can associate them together in different ways, and get the same number every time. So let me write out what I mean by that in a more formal way here. So for all elements A, B, and C in clock 8 arithmetic, it's going to be true that A plus B plus C, doing A plus B first and then adding that third number to it, is the same thing as A plus B plus C. So if you're talking clock something arithmetic, we can basically always assume that the associative property is going to work out because of this. It's always going to work out based on that. I'm going to give you an example. I gave you a verbal example. I'll give you a written one here just to kind of show you how that actually works. So let's say we started at 1 plus 3 and then added 6 hours to that. Is that the same? I'm going to put an equal sign with a question mark. Please do the same thing. So put an equal sign with a question mark. We don't know if it's equal yet, but we're going to check and see if it is. So is that the same as taking 3 plus 6 first and then adding an hour to that? What's 1 plus 3? In clock 8 arithmetic, it's 4. Still keeping the question mark here. I need to know if that's the same as 1 plus. This isn't going to be 9 now because 9 isn't allowed in clock 8 arithmetic. But 3 plus 6, if we go back to our arithmetic table, if you need to do that, you can think of the clock. 3 plus 6 is going to get you to 1, or you can think of it like this. 3 plus 6, match those up, that gets you to 1 that way as well. So this would be 1 plus 1. Now, is this the case? Is this true in clock 8 arithmetic? 4 plus 6. 4 o'clock plus 6 hours, that gets you back to, here's 4 o'clock plus 6 hours would get you back to 2 o'clock in a sense, and then 4 plus 6 hours, you look at the table, same thing here, 2. So we have 2 equals 2. Does this check out? It sure does, so I'll put a little check there, and I know that my associative property works out. So this is just a single case. We actually would need to check every case, but for any clock arithmetic, we're going to assume, because it does work out, but we're going to assume that associative property will work out in any clock arithmetic problem that we're doing. And then the commutative property is the last one. So the CIIA, and then an extra C at the end. Maybe you can come up with something clever, and let me know in class what you come up with to help us remember to check these 5 things for a commutative, potentially commutative group. So put the last C right there in a different color. Is the commutative property going to work? So we could look at the table and check that out. There's a couple ways we can think of this, but we're just going to use this trick. So for this one, I'm going to say both ways, but in the future, we're just going to use the trick and see if that actually works. So just a reminder what the commutative property actually says. It says that for all elements A and B, it's supposed to work out. So let's say in clock 8 arithmetic, it's supposed to work out that A, and we're doing addition here, so A plus B is supposed to be the same thing as B plus A. We're supposed to be able to go back and forth in a sense between the two, like commuting back and forth to work or to school, something like that. So clock 8 arithmetic, is it true that A plus B equals B plus A? Yes, it is. And we can also say, and from here on out, this is what I'm going to use instead. Also, the table is symmetric. I'm going to leave a little space to just do a quick example to show you the commutative property. Not something we'd have to do in future problems, but it's just something I want to show you right here. So also the table is symmetric about the main diagonal. And then just a quick example to show you just one instance of the commutative property working. You can look at that and say, is this true? 7 plus 6, does that actually equal 6 plus 7? Put a little question mark above the equal sign. So 7 plus 6, look at the table. The one that comes first is always the row, or the column, sorry, that you look at. So 7 plus 6, that's going to give me 5. Is that the same thing as 6 plus 7? That also gives me 5. So yes, it is. And so we can also look at this, see that there's symmetry across that main diagonal, and we could look at it this way too, and kind of think of it any one of those 3 ways, but from here on out we're just going to use this little shortcut. So 7 plus 6 was 5 o'clock, and this is 5 as well. So this checks out, at least this specific example. To check the whole thing, check the main diagonal. Because it works on the main diagonal, this also works. So is this a commutative group? I ran out of room here, but I can put this off to the side. Just put this underneath yours for me. Since I ran out of room, I'm going to put it off to the side here. I'm going to say, therefore, it's a commutative group. It's all 5 things checked out. And so now it's going to be time to stretch your mind a little bit more. it's just going to look weird at first, but once you get the hang of it, it starts to come pretty easy, I think. It should. So let's take this, and we'll talk about this, what I'm referring to by that, in just a second. But consider, write this down for me, consider a mathematical system defined as, or let's just say like this. So defined like this. And what I mean by that, like what, you might be asking, like what I'm going to put over here in the table. So this is our finite mathematical system. This right here, I just made this up. So you might be saying, what do you mean you just made that up? You can make up binary operations in groups? Yes, you can. So I just made this up, and I'm going to call this symbol the dope symbol. So when I say this out loud, I'm going to say dope, just like Homer would. So instead of addition, instead of saying this plus this is now going to be whatever the symbol or number I write here, dope this. So this is going to be 3, 5, 8, and 4. I'm not going to put my yellow lines here. I'm just going to keep mine nice and straight. But you can add rows and columns if you'd like to keep yours straight. And so 3, 5, 8, and 4, the same elements going here. And then 3 dope 3 is going to equal 5. 3 dope 5 is going to equal 8. 3 dope 8 is going to equal 4, and 3 dope 4 is going to equal 3. And then we'll just give you the rest of these. 5 and 3 doed together is going to be 8. And this will be 4. This will be 3. And this will be 5. You might be asking yourself, where are these numbers coming from? Why is this true? Well, I'm telling you it's true. I'm saying this is how I'm setting up the system. So we don't need to really know where it comes from, because this is just how I'm defining it. So this is just how I'm saying it works out. So this is 4, 3, 5, and 8. We're going to define those ones, those values like that. And this last one will be 3, 5, 8, and 4. Okay, so let's first identify that main diagonal. Let's circle this in a different color. And we're going to determine quite a few things here. So let's determine actually, I didn't want to write determine. I wanted to write just different parts here. So my fault there. I'm just going to say this is part A. We're going to list the elements. List the elements in the set of this mathematical system. So to do that, look at either this column right here, or look at this row right here at the top or on the side. What are the elements? I'm going to list them in numerical order as they would show up least to greatest on the number line. So 3, 4, 5, and 8. If you wrote them in a different order, that would be fine, as long as you got all 4 of them without any repeats. Okay, now let's do this to identify the binary operation. Well, the binary operation, I gave it a name. I didn't have to give it a name, but the binary operation is this symbol, which I'm calling dope. And so that's the binary operation. I boxed that in. The box isn't part of the binary operation. It's just whatever that means. Just like a plus sign, we gave that a certain meaning. The meaning of this is this table right here. This is what this means. 3 dope 3 gives me this. 8 dope 4 gives me 8, and so on. And so let's say part C here is going to say assuming the associative property holds. So we're going to assume that associative property is going to be true. Determine if the system is commutative. Or I should say is a commutative group. That's a different thing. So just to determine if it's commutative, we just need to look at the main diagonal and see if it's symmetric about that. But to determine if it's a commutative group, we need to check those 5 things again. So I'm going to be checking 5 things here. And I think the best way to do that, since I'm running out of space here, I'm just going to continue this example on my next flip chart, but you can just continue right underneath this. So on my next page of the flip chart, I should say. And so this I'm going to put first, just like I had before, think CIIA with an extra C. So closure. First going to check that. Put that off to the side in a different color. I'm using red. You use whatever color you're using. I'm going to check that first. So closure. Is the system closed? Everything here are those the only elements you also have here. And yes, that's the case. So we could say yes on that one. Yes, all elements in the table are elements in the system. And so that checks out. Closure is usually pretty easy to check. Just check the table, see if all elements in here were the ones that are along the top row, or the leftmost column. So let's check 2 now, the I parts. The first I part, we have identity and inverse. We're checking identity first. So is there an identity element? To check if there's an identity element, go back to the table and see if there's a column and a row that's identical to what you started with here. And if I look at this, it's the bottom row, it's the rightmost column. So last row, last column look exactly like what you started with. So the identity element is going to be 4, because you got 4 right here, you got 4 right here. So 4 do any number gives you that same number. 4 do any of these numbers gives you that same number here. So the identity is 4. So let's write that down here. 4 is the identity. And if you want verification of that, remember to see the last row or column. It's not always the last row or column, but it just has been so far for us. So identity, good to go. Put a little check mark there. Now I want to check the next I. I want to see if there's an inverse for every element. How do I check if there's an inverse for every element? I need to see that something, and then our operation is do, so I need to see that for every element that I have, 3 do something has to equal that identity element 4. What's that something for each one? So I'm leaving a space here for each one. 4 do something has to equal 4. 5 do something has to equal 4. And 8 do something has to equal 4. They all have to equal the identity element. So look at the table and see if there's something where that actually holds. So 3 do something, what's that something? 8 is that something for 3. For 5, the do 5 is 4. For 8, it's do 3. And then for 4, it's do 4, gets you back to 4. So 3 is 8. For 4, it's 4. For 5, it's 5. It's itself. And for 8, it was 3. Just double checking that. 8, 3, yep. So for 8, it was 3. So all these things get me back to that identity element. So 4 is identity. What number gets you back to the identity for each number? It's 8, 4, 5, and 3 respectively. So does each element have an inverse? Yes. Now we check for step 4, checking for that A, the CIIA, checking the associative property. Does it work? We would have to check every single case, which would be pretty tedious, pretty long. But remember what I told you in in part C, assuming that associative property holds. So we're going to assume that it holds. So let's write that down. We are told we can assume the associative property holds. But I feel like it's valuable if we check an example, so let's do that here just to get some extra practice. So let's check an example just for practice. Still write this down. So check an example just for practice. We'll put a little EX for the example we're checking. So let's check and see if 3 dope 4 in parentheses and then dope 5, is that the same as, so put an equals, the question mark, is that the same as 3 dope and then in parentheses 4 dope 5. Okay, so 3 dope 4, what is that? 3 dope 4 is 3. So here we put a 3. We still have dope 5. We still need to check that. Put an equal sign with a question mark. This is going to come down first, kind of like order of operations here. So 4 dope 5 is 4 dope 5 is 5. So we get a 5 here. I don't need the parentheses anymore there. And if it's the same thing here and here, this should work out. It's going to work out, but let's just see what 3 dope 5 is, and it is 8. So we're going to have 8 equals 8, and this checks out for sure. So this is just one example of many, many examples you could come up with. We'd have to check them all if we weren't told that we can assume the associative property holds to be able to say that yes, it does work, but we're told we can assume it, so we didn't even really need to do this. We just checked an example just for the practice there. So if it says you can assume it holds, you don't need to check it at all. You can just say it said we can assume it, so yes, it's good to go. So we have one more thing to check, the commutative property, that last C. So let's check the commutative property here and see if that works out. So we could check each example, but remember I told you that little trick. The trick was to see if it's symmetric about the diagonal, the main diagonal. So 8 and 8, that's the same. 5 and 5 is the same. 3, 3, 3, 3, 4, 4, and 8 and 8. There's definitely symmetry all the way through there. And so here we can say the table is symmetric about the main diagonal and so right there I will put a check mark. That works. All 5 worked. Therefore we can say it's a commutative group. So we're going to do a couple more examples together just to get some extra practice. The book has 6 examples. I'm doing 4 together with you here. I feel like this is something you really need to just practice a little bit more, practice kind of over and over again until you start to get the hang of it. Math is just that way quite often. You just have to put the time in before you start to understand it. So, for example 3, consider a mathematical system defined like this now. So you may have noticed I have kind of this UFO shape right here. That's going to be my binary operation here. So I'm going to put this little guy is my binary operator. Better like that. So it's a miniature UFO, and I use that just because I felt like using that. I could have used any old symbol I wanted to. The plus sign, the times sign, somebody chose to use that symbol to represent multiplication and addition. I'm choosing to use this symbol for this system. So here I'm going to have RST. Notice I'm not using numbers this time, which is allowed. It's just another system just without numbers. So I'm going to put RST in the asterisk. I'm not very good at saying that word. Asterisk. Asterisk. It goes there. And it's going to be defined like this. So R UFO R is T. R UFO S is going to be the asterisk. And then the rest will get filled out like you see here. So just fill out the rest as you see up here. RST. T with R is R, and then this continues RST asterisk and ST asterisk and R here. And so different colors, circle the main diagonal. You can check step 5 right now if you were doing a commutative group checking, see if it's symmetric, and in fact it is symmetric, so that step would check out. But for this one, or with this one, we're going to actually determine just some different parts of things. So we're going to determine, first of all, we're going to determine the set of elements first. So what is the set of elements? So the set of elements is everything that's here and it's everything that's here. These are the same things. They should be the same things. So the set of elements is just this. I'm going to put them in the order I see them listed, R, S, T, and the asterisk. So that would be your answer to that part. What if I said, part B here, what's the binary operation? Determine the binary operation. This is always whatever this symbol, picture, whatever that is up there. So the binary operation in this case is this little UFO symbol. That is our binary operation. Next we'll determine if it's closed or not closed, a closure, non-closure. In other words, you look at this and is everybody, or every element in the table, is that also listed in the set of elements itself? And yes, it is. And so we can say something like this. It's closed because all the symbols in the table are symbols in the set of elements. A few more parts here. Part D. What's the identity element? So determine the identity elements. If you look at the table, in other words, what elements do you see that gives you the same row, same column? So I look here, RST asterisk. Here it is, RST asterisk. So what element was that gives me that? T is. Let's check and verify that it's the same thing here with this column, and yes, it is. So the identity element should be T. That's what gets you what you start with. It gives you the same element as you start with if you perform this operation on it. And so E, what's the inverse of asterisk? So in other words, what, with the UFO applied to it, the binary operation of whatever the UFO stands for, this UFO what gives me T. So I'll look at this asterisk. Where do I see that matching up with T? Here it is. So asterisk UFO S gives me T. So what's the inverse of this? It should be S. And just as a reminder later when you look at this, why was that the case? Since this was true. Since asterisk UFO S equals T, and it works the other way around too. So just so we know that it works both ways. Asterisk or S UFO asterisk gives me T as well. And right here this was important. We had to get T because T was the identity element. So T is the identity element. Okay, I'm running out of space for parts F and G, so I'm going to make a new page. So this is still part of example 3. Just needed to go to a separate page. You just write it underneath what you already have. So F, what is this? Notice I'm not asking is it a commutative group or not. I'm just asking for particular parts of this right now. What is this and what is this equal to? So R UFO S and asterisk UFO asterisk. What are those things equal? To find this out, we just need to go back to the table. So let's find R first, and then UFO S, that is the asterisk symbol. So we have this equals this. And what's asterisk UFO asterisk? So here's this, this, and this. Put those together, I get R right here. So this should equal R right there. So pretty easy if you just go back to the table. And then part G, last part for this one, we're going to check what this is. So R, UFO S, and then after that we're going to do that first and then do this after that. What do you get with that? And to check one more, what is this? We're going to see if it's associative basically by doing this. At least for this particular instance, is it associative in this instance? So I'm associating things differently with the parentheses this way. What's RUFOS? We already figured that out. It was the asterisk. And then what's asterisk UFO asterisk? I already figured this out too, so I don't need to figure this out again. This should equal R. So let's check this as well. What's S UFO asterisk? That one I haven't figured out yet. So here's S. And then here's asterisk, that is T. So I would have R, UFO, and then a T. And then what's R, UFO, T? R, UFO, T is R. T is the identity element, so that should be the case. It didn't change the element I started with then. So this is an example of the associative property. That should go right there. So I'm going to do one more example with you. I feel like, hi Michaela Maroney, how you doing? We'll see why I chose that picture for this one. But if you need to, go back, pause, rewind. You may need to do that with this lesson more than some, because I realize it's just kind of hard to wrap your head around some of these things at first until you start to get the hang of it. So go back, pause, rewind as needed. But we're going to finish up our last example here now. So determine whether the following mathematical system is a commutative group under the operation, and my operator this time is going to be kind of a face with that little smirk on the face, or like I am disappointed type face. So that's going to go right here. Call that the Michaela Maroney face. Not with that little extra thing at the end. Something like that. And so each one of these probably will have a different looking personality to them, but it's just the kind of the sideways mouth thing going on there, the diagonal mouth. And so this one's going to be just 3 elements: X, triangle, and Y. I'm going to put the same things here, X, triangle, and Y. And this mathematical system is defined by this table like this. So I'm going to put an X here, I'm going to put triangle here, here, and here, and this is going to be y, x, and y here. This is going to be y, x, and y going this way as well. And so let's circle that main diagonal. It's a little messy there. I don't want to get rid of the x. There we go. Cover up the x. So there's the main diagonal. It is symmetric across that. So I know the commutative part works. If I notice that that didn't work, I might as well stop right there. No reason to go on if there's one part that didn't work. But we need to check those 5 things now again. So going back to those 5 things, first check closure. We got closure, identity, inverse, associative, and commutative. We're checking those 5 things. So let's use our different color for this and for this label things like that. So the CIIA with extra C, CIIAC. So closure, is it closed? Are all the elements that you see here also the same elements you see there? Yes, it is. So I'm just going to say, make things shorter. I think we understand, I hope we understand why at this point, why the system would be closed or not. So I'm just going to say that it is closed. If it wasn't closed, there would be different elements in here than what I have listed there. So that's good to go. Next we need to check identity. So let's check if there's an identity elements. And what is the identity element? You look here, is there a row that looks exactly the same as that? Right here. So the identity element is x. And that should be the same going this way and this way too. So here's the identity element, it's x. It's the same there. So the identity element is x. So that's good to go too. Now let's check step 3. So step 3 is to check there's an inverse for each element. Inverse would have to bring it back to the identity element x. So let's see if that does work out. So here's the extra I. So is there something for each element where we apply the not impressed operator that gives me the identity element x? So for x, for the triangle, and each one of these looks pretty sad. But just maybe yours will look a little more consistent than mine do. It's just hard to draw with this pen sometimes. Like that, looking kind of disappointed, each one, or just distraught, not exactly sure what that face would be called. So is there something that I can fill in here for each one of these where I apply this operator and it gives me x in each case? So x, let's see here, x, this, and x gives me x. So I would put an x right here. The triangle with the y gives me x. So the triangle with the y gives me x. And then a y with the triangle gives me x. So this would go like that. So is there an identity, or is there an inverse for each one? Yes, there is. So this checks out. And so I'll put a check right here. Now step 4. Let's check if the associative property works. Notice this time, unlike before, I didn't tell you you could assume the associative property is true. So we'd actually have to try a lot of different cases to show that every single case works. However, if you can find one case that doesn't work, you have found a counterexample, and then you can say the associative property doesn't work. So I tried some different things, and let's write this out. So we can't, I said this already, but I think it's important enough to write down. Not can't, but we aren't, sorry. We aren't told, boy, there we go. We aren't told we can assume it's associative so we need to check every case to say it is. However, if we can find just one counterexample, then it's not associative. And so I tried some different things, and I did find a counterexample. So let's write that down right here. This is my counterexample that I found. So I checked to see if triangle, then the face, then the triangle, then another face, associative like this first, was that equal to, so an equals with a question mark, was that the same as a triangle with the face, and then parentheses, the triangle again with the face. I left something out there, so I can squeeze that in. Meant to write face with y, sorry about that. So a triangle, and then a face over here again, and a y. So notice they're the same elements here, here, and here, they're just associated differently. So question mark right there. Is this the case? A triangle, face, triangle. What's triangle, face, triangle? That's another triangle. So this is triangle with the face, and then the y, is that the same as? So equals with a question mark, and then this triangle doesn't change with the face. What's the triangle, face, y? So here's triangle, face, y is supposed to be x. Need that parentheses there. So I'm going to put this. Is this the same as this? Now we need to check that. Triangle with the y is an x. Does x equal, is that the same thing as triangle with an x here? That's supposed to be triangle. Are these the same elements? No, they're not. So is it associative? It's not associative. So we could say not associative, and I'll abbreviate that like that. So it's not associative. That implies that it's not a group. And so this one, forgot to write my A off to the side here, but let's put the A in a different color. Does this one work? No, it doesn't. So I would put an X there. That doesn't actually work. We can assume then that it's not only not a group, but it's not a commutative group, but it's not even a group because the associative property didn't work. However, just to check and verify and practice one more time the commutative property, let's check all 5 and then kind of finalize our answer here. So this one, add one more page on mine because I ran out of space there, but just continue this under yours. We're checking step 5, is it commutative? And you could check every case, or you can just look at the table and check that sneaky, tricky diagonal way. I don't know if it's sneaky, but it's definitely a helpful little fast way to check. So x to x, y to y, triangle to triangle, that is symmetric across that main, or about that main diagonal. So I would say that this one, yes, this checks out because it is. So I'm just going to write, let's check for practice first, because we didn't actually need to check. Once we found out step 4 didn't work, we would know that we could stop there. So if you were doing a classwork homework problem, I wouldn't do this part because step 4 didn't work. If a step doesn't work, then you can stop right there. But let's check for practice here, since it's symmetric. About the main diagonal. Or across, about or across, meaning the same thing here. It's commutative. And so what do we say in whole, or with the whole thing? Is it a group? It is not a group because step 4 didn't work. So we can say it's not a, and I'm going to put commutative in parentheses because not only can we say it's not a commutative group, but we can even say it's not a group whatsoever because the associative property didn't work. So it's not a commutative group since step 4 didn't work. So let's box that in. That's our answer, and we'll write that as our justification since step 4 didn't work. Okay, so go back, pause, rewind, and refresh your mind, review things with this lesson if you need to. Also, please go to the book, check out those extra 6 examples. Something that I didn't mention before that I wanted to mention. Something that I didn't mention before that I wanted to mention is that this clock 12 arithmetic, looks like my slate might be running a little low on battery power here, so I got to use my little mouse on the laptop here. But clock 12 arithmetic for an example with clock 12. Let's write that with this example over here. Let's put this in a different color. Final thing I want you to write down. So clock 12 arithmetic example is on, it's a long example, it's on these pages here from 568 to 570, so it kind of overlaps those. Write that down here. That will help you with some of your classwork problems as well. So let me know if you have any questions in class, and please review things as needed. So always go back to any video that I make, review things as necessary. Don't be afraid to watch things more than once.